Okay, let's talk a little bit more about friction. We know that friction resists the motion if an object is already in motion, or it resists the attempted motion if the object is not actually in motion yet. So if we apply a force off to the right, then we would see that we would have a frictional force acting off to the left, resisting this motion. Or if the object were moving to the right, we would have a frictional force causing it to slow down by applying a force to the left. And the reason for this is that if we zoom in on the interaction between these two surfaces here, then we can see that it's a little bit rough. No surfaces are perfectly smooth. And so there are two ways in which this upper block can move relative to the lower block. And the first of these ways would be that if this material, the material on both the blocks were to actually break off. So we would have to have, this piece would have to break off, and this piece and this piece and down here, and we would have to have, the material would actually have to break in order to have one block move relative to the other block. The second way would be that as this block moves along here, then it slides up, so it goes over these little bumps. And so essentially we'd have to lift this block up so that way there would be some space underneath for it to move. And so we have a couple things relating to friction here. So one is how rough these surfaces actually are relative to each other, and we call this the coefficient of friction. So we have here this coefficient of friction, and we symbolize this with this Greek letter mu. It's like a curvy little m there. So this is the Greek letter mu, lowercase. So this coefficient of friction describes the roughness between two surfaces. It's found experimentally just by moving one surface relative to the other and finding how much force resists this motion. And so you need to know both surfaces. If we have, ice on ice, then the coefficient of friction is very low. If we have sandpaper on rubber, then the coefficient of friction is very high because the sandpaper would kind of stick in that rubber a little bit. So the coefficient of friction is always between 0 and 1. It's always somewhere between there. And we also have another bit that the frictional force is related to is the force that is pushing these together. And so essentially the normal force. There's some force pushing in here and some force pushing down here. And the greater this force is, the greater these are smashed together, or the greater the force that this upper block would have to overcome in order to move along. And this is the normal force between the two surfaces. So it's not only related to the roughness, which is described by the coefficient of friction, but it's also related to the normal force. And I apologize, this should be a lowercase n here, the normal force. So these are the two things in which our frictional force is related to. We have the frictional force, the magnitude of the frictional force is equal to the coefficient of friction times the magnitude of the normal force. And this is in general. We actually have here two specific types of friction. We have static friction, and we have actually, here's a picture. If we have a large normal force, then these are smashed together and a lot of material is going to have to break, or we're going to have to lift this up a lot. If we have a small normal force, then not as much of that takes place. The two different types of friction that we have are static friction. This is the friction for an object which is not yet moving. And we have kinetic friction. So this is the friction for an object which is moving. And when an object moves along, it would be more like this upper picture here. If this upper plate is moving relative to the lower plate, then as it moves along, it gets a little bit of like air trapped underneath here and whatnot, and it'll glide a little bit on this bed of air. Versus if it's not moving, then this air is kind of pushed out, as we see down here. And so you can think of like an air hockey table. When the air is on, then the puck is ready to move without much force. When the air is off and it's sitting flat on the surface, then it doesn't move as readily. So the way we differentiate between this static friction and this kinetic friction is through their coefficients of friction. We measure different coefficients of friction for the static case and for the kinetic case. And so the static friction, we use a coefficient of static friction, and for the kinetic friction, we use a coefficient of kinetic friction. And then we define here the magnitude of the kinetic friction force is equal to the coefficient of kinetic friction times the magnitude of the normal force. Or this is generally more often written, the kinetic friction force is equal to mu k times the normal force. But the normal force is a vector and the frictional force is a vector, but these are not the same direction. This only represents the magnitude. The frictional force is always perpendicular to the normal force, because if you remember, the frictional force is parallel to the surface and the normal force is perpendicular to the surface. So the kinetic friction force is just simply the coefficient of kinetic friction times the normal force. And you would need to be given the materials and then look up what the kinetic friction coefficient is, or just be given the coefficient of kinetic friction. The static friction force is slightly different. We have to write our static friction force as an inequality, and our static friction is less than or equal to the coefficient of static friction times the normal force. And again, these are magnitudes. Static friction is parallel to the surface as well. And the reason we have to write this as an inequality is that if the object is not moving, and we don't apply a force to it, then there would be no frictional force. If I have a box here, which I apply no force to and sitting on the surface, if I apply no force, then there wouldn't be a frictional force to push it one way or the other. That just wouldn't make sense. Then we would have boxes spontaneously moving. But if I apply a force in this direction, then we would have a frictional force pushing back this way. And there is a maximum amount. Let's say that my maximum friction force, Fs, maximum static friction force, Fs max, is equal to 10 newtons. If I only push with 9 newtons here, then our static friction force would only be 9 newtons. It will only resist motion. It won't cause motion in the opposite direction. It wouldn't make sense to say friction is 10 newtons and the force is 9 newtons, then I could push on a box and have it move, the opposite direction of the force, which wouldn't make sense. So we have to write it as an inequality. Most times we will talk about the maximum static friction force though. So the maximum static friction force will be equal to the coefficient of static friction times the normal force. And again, these are magnitudes as well. And so the maximum static friction force is the maximum force it can resist motion. As soon as we apply a force greater than the magnitude of the static friction force in the direction opposite the friction, then this will overcome the friction force and it'll start moving. And once it starts moving, then we would change our frictional force to be the kinetic friction force. So again, if our maximum static friction force were 10 newtons and we came over here and applied 11 newtons of force, then it would start to move off to the right, and in which case then we would use the kinetic friction force after it started moving. So key words in which we would be looking for the maximum static friction force. If we say something is on the verge of slipping, or on the verge of moving, then it means that the static friction force has been maximized, and if we apply any more of a force, then it's going to start to move. Okay, so those are friction forces. And there's also, in addition to just the roughness of these two, there's also some molecular interactions, atomic and molecular interactions going on here between the two surfaces as well. If I have one surface moving this way, and then I have it's moving relative to the surface, then there is some interaction between these molecules. However, the roughness of the two plays a much larger role than the atomic and molecular interactions there. So to summarize, we have the frictional force is parallel to the surface, which is perpendicular to the normal force, and the static friction force is the coefficient of static friction times the normal force, less than or equal to this, and the kinetic friction force is equal to the coefficient of kinetic friction times the normal force. So oftentimes when we're solving problems, we'll need to look at the y direction first to solve for the normal force before we can find our frictional forces and solve in the x direction.